You've probably heard of RAM before, but what is it, and why is it so important? Stay tuned, because today we'll be adding some RAM to our custom CPU, which will greatly expand its capabilities. Hello everyone, my name is Mike and you're watching Polymath Unlimited. In this series, we are building a Logisim simulation of an 8-bit CPU with the following design goals in mind. First, the CPU should be simple enough to make a physical build practical. Second, the CPU should be capable of complex operations. And third, the CPU should be easy to program. In the last episode, we learned how to build memory circuits using master-slave flip-flops, and we used those circuits to add a register to our CPU. In today's video, we will learn about RAM and how to add support for large amounts of memory to our CPU. RAM stands for Random Access Memory. Random access just means that we can access any location within memory with the same time delay as any other location. By contrast, older forms of computer memory, such as magnetic tape memory, are not random access because they can only read memory in the order in which it was written, and it takes time to change the read head to a different location on the tape in order to access a different portion of memory. Disk drives are still technically random access, but they are still fairly slow by comparison because it still takes time to physically move the read head to a different part of the disk. This is why, in most computer systems today, the computer's main memory is RAM. This is where the computer stores both data and code that it is currently working on. This gives the computer very quick access to the data it needs immediately. Other data that we need to store long-term is typically stored on the system's hard drive, which is usually either a disk drive or, more commonly nowadays, a solid-state drive. To understand how RAM works, we can think of the memory space as being divided up into several cells, each of which can store a number. Each cell in memory is given a specific address. In order to access or modify a value in memory, we need to give the RAM unit an address as input. We also need to give a read input and a write input so that we can tell RAM whether we are reading or writing data to or from that memory cell. Finally, we will have some data input-output lines. These lines will be used to both read data from memory and to write data to memory. Now, we could build our RAM out of logic gates, just like we did with our register. However, if we want any appreciable amount of RAM, this would quickly make our circuit become much too large and cumbersome to be usable. So we will break away from our usual logic gates only approach for now, and use Logisim's built-in RAM circuit block. This contains all of the functionality we need for our RAM, but all in a much smaller, more manageable package. In the options for this circuit, we will change the data interface to one synchronous load store port, since this will closely mimic the behavior of the real RAM chips we will be using when we build this CPU for real later. Since we are building an 8-bit CPU, we will leave the data width at 8 bits. However, an 8-bit address space only gives us access to 256 different locations in RAM. While 256 bytes is more than enough to run some simple programs, I would personally prefer more memory than that so we can run some more complicated programs if we want to. We will therefore increase the address width to 16 bits, which will give us the ability to access up to 64 kilobytes of RAM. In order to make it so that our CPU can access RAM, we need to add two new registers. We'll call these registers address high and address low. These registers will contain the first 8 bits and the last 8 bits of the address we want to access, respectively. We'll connect the values stored in these registers to the address lines of the RAM unit. We'll also add some read and write inputs, and connect them through some logic gates to the RAM unit's select and load inputs. I'm really not sure why Logisim has its RAM circuit set up this way, since most RAM circuits that I've seen have just the simple read and write inputs. Regardless, this will let this RAM unit behave just like the real thing we will use later during the physical build. Now that we have multiple registers and the ability to access RAM, we will need to add a data bus to our CPU. A bus is simply a generic term in computer architecture for some wires that we use to transport data from one location in our computer to another. For our data bus, we'll simply use 8 wires. Each wire will have a pull-up resistor attached to it. This will make it so that the data bus will always contain all ones unless something else pulls the data wire to ground. To illustrate this, let's make it possible to have the accumulator send data out onto the bus. We'll start with 8 NAND gates, one for each bit of the accumulator. Now, we'll attach the inverted output of each accumulator bit to a NAND gate's input, and all of the other inputs will get wired to a signal that we will call accumulator output, or AO for short. Now, whenever we turn the AO input on, the NAND gates will output the value contained in the accumulator. If AO is off, however, then the NAND gates will simply output all ones. In order to get this to work in Logisim, we need to set each of the NAND gates' output settings to 0/floating. This will make it so that the gate only pulls its output low, and then when the gate is on, it simply does nothing to whatever wire it is attached to. This is a concept called open collector logic, and stems from the days when bipolar junction transistors were used more commonly than MOSFETs in computer hardware. I'll go ahead and label all of these NAND gates OC in order to distinguish them. Now, if I connect these outputs to the data bus, we can see that I can now put data from the accumulator onto the bus. This means that we can now move data from the accumulator to any other part of the CPU that is also connected to the data bus. Let's connect our ALU's B input, the address register's data inputs, and the RAM module's data lines all to the data bus. For now, we will also connect some input pins to the data bus so that we can manually put data onto the bus. These will be useful for the initial phases of debugging, but we can remove them later. Note that these input pins also need to be set to the tri-state configuration, allowing us to make them output a floating value while we're not using them. Now, to illustrate some ways that our CPU might use RAM, let's do some simple operations. We'll go into our RAM unit and modify the values at address 0 and address 1 to contain 42 and 53. Now we'll manually set the data bus to 0 and enable both the high and low address registers' input enables. Now, when we cycle the clock, both address registers will contain a 0, and they will therefore be pointing at address 0. Now we'll turn off the address register's input enables and turn on the read signal and the accumulator's input enable. When we cycle the clock, the value of 42 contained at address 0 will be loaded into the accumulator. Now we'll turn off the read signal and the accumulator's input enable, set the data bus manually to 1, and turn on the address low register's input enable and cycle the clock. Now we are pointing to address 1. Next, we will turn everything back off and turn on the op signal, the read signal, and the accumulator's input enable, making sure that the op code that we are sending to the ALU is 0. Now, when we cycle the clock, the value 53 contained at address 1 will get added to the value 42 contained in the accumulator, and the accumulator will now contain the result of 95. Now we'll set the data bus to 2 and load the value into the address low register just like before. Finally, we will set the write signal, the accumulator's output enable, and cycle the clock. The value 95 should be written from the accumulator into RAM at address 2. We have just added the value in address 0 to the value in address 1 and stored the result in address 2. Now that our CPU can access RAM, we have opened up a whole new world of possibilities. In most computers, both data and program instructions are stored in RAM. This means that we will need a way to tell where in RAM the CPU should get its instructions from. For that, we'll need a new type of register called a program counter, but that will have to wait until the next video. Until then, feel free to play around in Logisim and see what you can create. Thank you for watching, and I will see you next time.